Some announcements. Homework number 3, I just need to make one additional change to that, and then I'm going to post it on Blackboard this afternoon. It'll be due on Friday. It's going to cover softening, which we did on Friday of last week, and then ion exchange and reverse osmosis, which is today. So it'll be a relatively short assignment since it's only covering 2 lectures worth of material. We've got a midterm exam on Monday, and I've already told you a little bit about the parameters on that, so just remember a week from today is the midterm. And just to get you in the midterm mindset, we're going to have a quiz in class on Wednesday. So it will be covering, it'll be just, I think, our second quiz of the semester. So it'll be covering the material since our first quiz, which was those lectures that I was gone. So I think the first quiz was during class number 5, so it'd be from class 5 to class 12, which is today. For the quiz, that's closed note. If you need any formulas for the quiz, I'll provide them on the quiz paper, so you don't have to bring any kind of equation sheet or textbook or anything like that for the quiz on Wednesday. Any questions on the announcements? All right. So today we're covering the basics of ion exchange and reverse osmosis, and that material is in chapter 8 and 9 in your book. All right. So remember that in class previously, when we were talking about softening, we discussed that one method to achieve softening is by precipitating out the calcium and the magnesium that contributes to hardness. And the way that we could accomplish that, as we talked about on Friday, was through the addition of caustic chemicals that increase the pH, like lime, for example. And when the pH is increased, then those materials precipitate out, and the water doesn't have the polyvalent cations that contribute to hardness. Another way to achieve softening is through a technology known as ion exchange. And in ion exchange, what we're doing is rather than precipitating the hardness from water, we're replacing it with an equivalent amount of charge, but with something that is monovalent instead of something that is polyvalent. Now, ion exchange is usable for more than just hardness removal. We can use this technology of ion exchange, for example, to remove toxic metals in addition to metals that contribute to hardness. And it's not just something that we can use to remove cations. Ion exchange also can be used for removing negatively charged anions and substituting out the negatively charged ions that we want to remove from water with other ones that are benign, that we're less worried about them being in the water. So what it says here is that you are exchanging a charged ion with an equal charge of something that is electrostatically attached to an immobile solid particle. So this picture is of a typical home ion exchange system, a water softening setup. And so you can see that the raw water is coming in here from the right. The raw water comes in and first goes through a media filter that's probably just removing any kind of sediment. They have all sorts of different cartridge filters, but the most common would be like a spiral wound plastic that the water passes through, and so big particles of sand and maybe a little bit of suspended iron that had precipitated out in the pipeline could be trapped by that. And then the water goes through this. On the left is a big tank that has these little plastic beads in there. And the plastic beads can vary anything from 0.04 millimeters to 1 millimeter. But inside of the bead is this hollow structure that has functional groups that ions are attached to. And so here The water goes through the ion exchange, and it has lots of calcium as it enters the ion exchanger, and then the calcium gets stuck onto the media, and for each calcium that goes on and gets stuck, 2 sodiums are released. And so the water that comes out has more sodium in it than the water that came in. But it has less calcium, which means that it has had the hardness reduced. Now this other tank is just full typically of rock salt. So pellets or granules of sodium chloride. And the purpose for that is that ion exchangers don't have an unlimited capacity of sodium ions attached to the functional groups. That over time, when they become saturated with calcium, then the calcium increasingly passes through without being removed. And so you have to turn a regeneration step on and kind of flush out the calcium and waste that water to the sewer. And as you're flushing out the calcium, you do so by putting a really concentrated brine solution, really high sodium chloride. So we'll talk about an overview of this process and do some related calculations, but this is where you're most likely to see ion exchange in the home. Sometimes this is called a point of entry ion exchange, where typically you'd be treating all of the water that gets consumed in the house, whether it's used for washing clothes or drinking or flushing the toilet. All of the water in the house is being treated if it's a point of entry system like this. Of course, there are certain things that you don't necessarily care if there's hard water. You may not care if the toilets have hard water, for example. Maybe the only thing that you'd want to have soft water for would be your dishwasher and your clothes washer. And in a case like that, it might be more economical to have something called a point of use water softening. And so it's just a matter of the piping and whether some of the water coming into the house is bypassed without being treated first. And so point of use versus point of entry. Point of entry is the most common, just because people don't want to have multiple parallel water systems in their house, one that has been treated and one that hasn't. Okay, so these ion exchange resins are made out of polystyrene. And you may have heard of polystyrene before. It's what hamburgers used to come in. They don't do that so much anymore, but back in the 80s, when I used to go to McDonald's, when I was out there banging, you'd have hamburgers in these polystyrene containers, and they decided it was not very friendly for the environment, because the way that they made them released a lot of chemicals into the atmosphere that actually consumed the ozone layer. In addition to refrigerants, the manufacturer of polystyrene put these chlorofluorocarbons into the atmosphere. So I think they've reformulated polystyrene production so chlorofluorocarbons aren't used quite as much anymore, because polystyrene is still used in like plastic peanuts and like packaging for computers and TVs and stuff like that. But I'm sure everybody knows what this stuff is. And so polystyrene is the main structure of it. But then inside the polystyrene, they have divinyl benzene. Now the divinyl benzene is kind of the glue that holds everything together on the inside structure, so that there's some place that these functional groups can attach to. I've got a blown up view of this diagram on the next slide, but if we zoom in on the polystyrene, what we would find is these sites that have these functional groups that are able to attach sodium or calcium or a cation, for example, for what are known as acidic functional groups. And so acidic functional groups like sulfonate or carboxylate are the sites to which the cations are affixed. And in basic functional groups, that is where the functional group has a net positive charge, and then an anion would be temporarily absorbed to it and then exchanged. So most common would be a strongly acidic functional group. And sulfonate has this negative charge on it. And so on the inside, let me just quickly jump forward to here. On the inside of the structure, is the functional group, which is a minus sign, and it's permanently attached to the media. The minus sign, it's not going anywhere. The sulfonate is permanently bound to the exchange resin, but there are these only temporarily affixed cations. And so when a resin is brand new and it's just gone through the regeneration cycle, then it would be completely saturated with sodium ions. But then as the water that's to be treated is going through, passing all around these beads, think about it, we've got this gigantic tank, it's just full of beads, these little plastic beads. And so the water is flowing down through this collection of beads, and it's having to absorb into the membrane layer around the outside of the polystyrene, and it's having to penetrate into the interior area, and then that exchange reaction has to occur, and then the replacement ion has to penetrate through the membrane layer and out into the bulk solution. So it's not an instantaneous process. There is a diffusion that takes some time, and that's kind of why for a small pipe, if you look at the diameter of the pipe that the water flows through is very small. But the diameter of this tank, the cylindrical tank that has all these beads, it's large because the water is going to be flowing around these beads at a relatively low velocity in order to provide enough time for that exchange reaction to occur. So the density of the functional groups inside of the polystyrene, as well as the flow rate that you're being treated, kind of determines how long it takes before regeneration of the solution is required. Okay, so here's this zoomed in view again. Remember I was talking about how there's a diffusion that has to occur before we're able to remove the hardness, because there's all this positively charged calcium on the outside that is needing to pass through a liquid layer that's on the outside of the polystyrene bead. And so in fluid mechanics, you maybe remember the no-slip condition that, just to refresh your memory, if we have a river and there's water that's flowing through the river, down here next to a stationary surface, the velocity is actually 0. The velocity of the water is the same as the velocity of the surface that it's flowing next to. And so the same thing is true here with this bead. If the water is flowing around the bead, there's this liquid layer on the outside of the bead that isn't moving. And so the calcium has to diffuse across that layer before it comes in contact with the polystyrene bead. And then the water has to penetrate through the pores of the polystyrene bead to get at the functional groups, which are on the inside. The functional groups are on the outside, but also on the inside. More of the functional groups are on the interior of this exchange resin than on the outside of it. And so then once it gets into the functional group, and the calcium is more strongly attracted to the negative functional group than the sodium is, and so the calcium comes in and displaces the sodium, and then the sodium has to migrate out through the pore, through the membrane, and into the bulk solution. So it's a time-consuming process. Movement of the target ion, and I'm calling this calcium the target ion because that's what we're hoping to remove. So it goes from bulk solution to the boundary layer, which here is in this light orange, before it gets to the ion exchange media. Then diffusion through the boundary layer. Then diffusion through the resin to the exchange site. Then there's the exchange reaction. Then diffusion of the exchanged ions. And so the exchanged ion here is sodium, outward through the pores and then out through the boundary layer, and then once it's out of the boundary layer, then it's in the bulk solution. So I guess on the right hand side of this diagram we'd show some calcium but also some sodium, because one bead in particular is not going to remove every single calcium that flows next to it. That's why we have to have thousands and thousands of beads that the water is flowing around, is that, you know, you may have this calcium that gets removed by this media, but then all the others are just going to flow around it until there's an available space that has been vacated by sodium, and the calcium can come in and take the space. So you can see here that the size of these media can vary a lot depending on what's the target ion and what are the functional groups that are being used. Any questions so far about ion exchange? Now, one of the tricky things about ion exchange and the fact that it isn't a permanent process is that as the functional groups get saturated with the target, then an increasing amount of the target is going to break through the end of the column. So initially, let's say at the very beginning when this has plenty of sodium in the media, very little calcium is going to make it through the end of this gauntlet. You know, water's flowing around the edges of this porous media, and very little calcium would make it through when all of the beads are fully loaded with sodium. There's going to be some opportunity for the calcium to encounter a bead that's ready to accept it and for that exchange reaction to occur. But the further down into the depth of the column the full saturation of the resin by the target ion is, then the higher the concentration of the target ion in the effluent's going to be. So there's just a finite number of ions that can be removed at any particular place. And this breakthrough curve just illustrates that as time goes on, you may start off with a really low concentration of target ions in the effluent, but gradually there's going to be some of the ions that get through the flow path and they haven't encountered an available resin site. They've flowed through it, and just probabilistically there's going to be some functional sites that are full the entire path, and so there was just no opportunity to get swapped for sodium. And then the probability keeps getting higher and higher as time goes on, and this breakthrough curve is just kind of a representation of how much target ion is in the effluent. And so C naught is the initial concentration, and then this just shows that ultimately you're going to get right back up to a completely saturated with calcium functional group through every path, and therefore there's no removal of the target ion. And so what we need to do is we need to decide how much of this breakthrough is acceptable to us. And then you would design your redundancy based on whether you're trying to remove some sort of a toxic chemical that you have no tolerance for. Like if we're removing arsenic, maybe we would have less of an appetite for breakthrough than if we're just removing calcium, because we prefer soft water when we shower. So if it's an aesthetic concern compared to a human health and safety concern, then the amount of breakthrough that can be tolerated would be highly variable. Different cations are more strongly attracted to the functional groups than others. And this table kind of illustrates how different cations, how attracted they are to the functional groups. And so, for example, a strong acid resin, you can see that the most strongly attracted cation to that resin would be radium. Barium, lead, they have really high ratios of the this alpha factor you can think of as the preference for the functional groups compared to the functional preference for sodium. And so sodium is the baseline. So this is kind of a linear scale of where calcium is 1.9. That means that the resins have a relative attraction for the calcium as compared to sodium of about double. And this has a quantitative implication that we'll use in an example here in a moment. This alpha factor is what you can calculate you'll use it in calculations that have to do with how much water you can treat for a certain volume of media before the media is completely saturated. Now, in the equations that are found in the book, they differentiate between the counter ion, I, and the presaturant. And they don't do a very good job differentiating between what they mean. But just think about, in this example of water softening, then our counter ion would be calcium, because that's what we're trying to get rid of. And the presaturant, meaning the ion that the resin functional sites are presaturated with before treatment occurs, is the sodium. So J is the presaturant, and then the definition of X versus Y is Y is the resin and X is the water. So this ratio is basically just an indication of how much of the ion would be on the functional site versus how much of it would be in the water for the counter ion versus the presaturant. So if you put the resin into deionized water and it came into an equilibrium of, the same amount was in solution as was on the functional sites, this equilibrium factor is alpha. So we'll use this in this example. And this is going to be pretty closely related to one of the problems that's on your homework for Friday. So let's say that we have a strong acid cation resin that we're using to remove hardness. And so we know the volume of resin that's available. Remember that tank that we saw in the picture here? So we're saying that the volume of the tank is 0.055 cubic meters. So that's the volume of the tank that has the resin beads in it. And this particular resin has a rated Q sub T capacity. For every liter of beads, then it has a total capacity of 1.9 equivalents of calcium carbonate. That's just a measure of overall the total amount of calcium that could be absorbed to the media functional sites. And we're using this to remove calcium, and what we know is that the water that's going through to be treated has 150 milligrams per liter of calcium as calcium carbonate and 21 milligrams per liter of sodium. So this is just the water that comes into the house, has a medium amount of hardness. 150 is just that middle range. And then it's also got a fair amount of sodium in it. Now, as you might expect, if you're using sodium for the presaturant, then how much sodium you've got in the water that enters the ion exchanger is going to affect the efficiency of the exchange reaction. Like if you've already got a lot of sodium, then the sodium isn't going to be able to come out of the resin as easily as if you've got a water with no sodium in it to begin with. And so in part, that's what this Q sub T and what we'll calculate here, the Q sub Ca, also takes into account. All right, so let me demonstrate these calculations. Now, we've talked about milligrams per liter a lot this semester, and we've done some calculations to convert into as calcium carbonate. But what we haven't done is taken milligrams per liter into milliequivalents per liter. We've kind of talked a little bit about equivalents, but let's do that as step A. So we have here in step A 150 milligrams per liter of calcium carbonate. And what we know about calcium carbonate is it is 100.086 milligrams per millimole, because it's 100.086 grams per mole for calcium carbonate. So I'm going to convert here into 1.499 millimoles per liter of Ca2+. So that's how much calcium we've got. And this was, by the way, 150 milligrams per liter as CaCO3, because that was the units that it was already defined as, 150 milligrams per liter as CaCO3. So we converted into the number of millimoles per liter of calcium, and then for every mole of calcium, we've got 2 moles of charge. And so there's twice as many mill equivalents. So there's 2.997 mill equivalents per liter of calcium 2+. Now the sodium's a little bit easier because we don't have a difference between the number of moles and the number of equivalents, but for the sodium it's 21 milligrams per liter of sodium, and the molecular weight of sodium is 22.99 milligrams per millimole. And so then that tells us that we have 0.9134 millimoles of sodium, which is 0.9134 milliequivalents per liter for sodium. So how many moles of charge have we got? And let me just, because I'm recording this lecture, bring the solution so far up onto the screen. Get it recorded into the video. Here it is. All right. So any questions so far how we converted from milligrams per liter into mill equivalents per liter? So we're just converting the quantities into the units that we'll need them for the rest of these other steps. Okay, now here for part B, we're trying to determine the separation factor, alpha. Okay, so the separation factor for sodium over calcium. Now, what we have here is calcium is the counterion and sodium is the presaturant. This table gives us the alpha, but it is the alpha of, let's just see, it's going to be calcium over sodium. So the alpha of calcium 2+ over sodium plus from the table is 1.9. So the calcium 2+ down below and the sodium up above is just going to be 1 divided by 1.9. So it is 0.5263. And the reason why we are calculating that inverse is because down here it is wanting to know the sodium above calcium here. So we just needed to find the inverse of the calcium over sodium because that's what is going to dictate the overall capacity per liter of resin functional sites to treat water. So this is kind of just an intermediate step that we're using for part C. So we were given the calcium over sodium. We wanted the sodium over calcium. It's just the inverse of the amount from the table.
Is the separation factor unitless?
Yes, it's a ratio. Okay, let me erase this so far just so I can continue. Anybody need me to pause for a moment? All right, so part C, what we're calculating here is the maximum useful capacity. The Q sub Ca. So the Q sub Ca is, you see the formula on the screen there. I'm going to do the substitutions here. So in the numerator, it is the 2.997 milliequivalents per liter. That was the concentration of the calcium. And then we're going to multiply that by the total Q sub T. So 1.9 equivalents of calcium carbonate per liter. So everything else that we've calculated so far has been milliequivalents. So I'm just going to say that is 1900 milliequivalents per liter. So this Q sub T is something that's defined. It's like a property of the ion exchange media. It would be a given from the manufacturer. So they say that this particular resin bead has a total capacity of 1900 milliequivalents per liter. So now down in the denominator, we're going to have the concentration of calcium, which is 2.997 milliequivalents per liter, and then add that to the concentration of sodium. So now this is where it comes into a play that it's not just about how much calcium is in the water, but the effect of sodium is felt as well. Okay, let me pause for a second and have you calculate this. What is going to be the Q sub Ca? This is going to have units when you do calculate it. Let me write just what the units are going to be. It's going to be units of milliequivalents of calcium 2 plus per liter of resin. Overall, this resin can handle 1900 equivalents of calcium carbonate per liter. But in a situation where we also have sodium in solution, then that's going to reduce the amount of capacity that can be used for calcium. So this part C, what we've basically done is we've said, on a practical basis, taking into account that calcium isn't the only ion in solution, we're going to have a little bit lower capacity than the overall total capacity that's rated by the manufacturer. And then the last step here in part D, what we're doing is we're finding out how much water you could treat before recharge is needed. And so the maximum amount of water that can be treated is this 1637 milliequivalents of calcium per liter of resin. And we have that the concentration of calcium is, down at the denominator, I'm just putting the concentration of calcium, 2.997 milliequivalents of calcium per liter of water. So then that gives us 546.2 liters of water per liter of resin. And of course, we have 55 liters of resin in that tank. So let me just bring this last part up on the screen. Okay, so we've got our alpha factor calculated, the maximum useful capacity, and then to find out how much water can be treated, then you just multiply the 546.2 liters of water per liter of resin by the 55 liters of resin. That's the volume of beads that are in that tank. And that suggests that we should be able to treat 30,000 liters of water before all of the functional sites are exhausted. But remember, this takes into account the assumption of perfect exchange. And what we know is that there are going to be some water molecules that could flow through here and escape without getting the calcium removed. So to achieve like this perfect transfer, you'd have to have an infinitesimally slow movement of water through the resin so that there would be 100% exchange between the calcium and the sodium, and there'd be no breakthrough. But this is kind of like the perfect world scenario, is that you'd get 30 cubic meters of water if there was perfect exchange between the calcium and the sodium in this scenario. Okay, so that's just an example of some of the calculations that get done when it comes to ion exchange, and this is maybe that would be something that you could time your regeneration on. So if you know in theory you should be able to get 30 cubic meters, assuming perfect transfer, and of course there never is perfect transfer. Like if you had it regenerate when you got halfway through your volume, if you had it regenerate the resin after you treated 15 cubic meters, then probably you'd avoid the worst of the breakthrough.
Is there not a way you can calculate this based on residence time that will give you a more realistic result?
We could convert, if we knew the water flow rate, we could convert this into a time.
Okay.
We could calculate a time, but then that would be assuming perfect transfer. And so you'd still need to have the resin regeneration prior to that time, because you'd start to see particles escaping through without getting treated. Now just a couple of practical concerns when it comes to ion exchange is that these beads are small, and so that they can get crushed through the weight, and when they're really small, there's going to be head loss of water flowing through them. If you have chlorine in the water before it goes through the ion exchange, that can damage the polystyrene and can degrade the functional sites through oxidation. And these systems are also sensitive to the precipitation of iron and manganese, the accumulation of sediment, and so it's suggested that iron and manganese concentrations are relatively low and that the turbidity should be low before it goes through, because if you have a lot of particles, then that would interfere with the movement of ions across the membrane if there's particulate matter in there, because the ions wouldn't be able to migrate through or around a particulate coating on the outside of the membrane functional groups. There is a cycle, a regeneration cycle that you go through with ion exchange, where during treatment the raw water is flowing downward and hardness is being removed. But then when the breakthrough is too high, there's this process of preparing for regeneration. And the first step to prepare for regeneration is that instead of having the water go down through the column of beads, you send the water upward through the column of beads, and you try to suspend the bed. If you send the water up fast enough, then it'll cause this media to kind of float. The velocity is just kind of suspending the particles temporarily and has them banging together a little bit. A little bit of abrasion is a good thing, because it could remove any sort of a scum or biofilm that's accumulating on the outside of the of the filter. Sediments could be shaken loose, and that backwash period is usually 5 to 15 minutes is plenty to get rid of any of the debris that's accumulated. And then during the regeneration phase, you're flushing a high concentration of the regenerate, which is, in our case, for softening type ion exchange, would be a concentrated sodium chloride solution. And it takes usually 30 to 60 minutes to give adequate time for the concentration of the sodium to penetrate down through the membrane and replace all of the calcium. Because although calcium is preferred at those functional groups, when the concentration of sodium is high enough, you can still force the calciums out, and then then you'd end up wasting the regenerate water because it's a really high concentrated solution of salt, and it's got the calcium as well, so you just waste the water that's coming up during the regeneration cycle. Then, of course, because you've got so much salt inside of the resins, you need to rinse it out with fresh water and waste the water that is going through the column during the rinse phase. And then after rinse, when you've gotten the regenerate out, then you can return it to service, and then it's good for capturing the hardness once again. Depending on how the water is going to be used, it may be worthwhile to have some redundancy built into the system, where a 3-column setup is fairly common if you want to have continuous service, because you would always have 2 of the columns connected in series, meaning that the water comes into one of them and then into the other, with one of the columns out of service and it's going through that regeneration and preparation cycle. And then this first column is the one that would become fully saturated first, fully saturated with the target ion. Then you'd take it out of service, and then this column, what's right now column 2, would become the primary upstream column, and then it would go to column 3. And so you kind of have your cleanest and most freshly regenerated column being the one that's downstream of a more recently, of the column that is becoming in the process of becoming fouled. And then that would help to limit breakthrough. Everybody here has already taken environmental engineering, and I'm sure that Dr. Yoon did some mass balance calculations with you, probably during like the water quality, where you're talking about mixing different rivers together and the concentration of different constituents. And that same kind of math is used for figuring out what fraction of treated water to mix with raw water if you're aiming for a blended concentration that's somewhere in the middle. And so you would use the same kind of, my formula got changed a little bit here. It's basically, since we're running low on time, I'm just going to have to illustrate this calculation for you. This is an example which says if we had water that's coming out of ion exchange that's 5 milligrams per liter, and we're mixing it with raw water, and we're trying to achieve a blend of 115 milligrams per liter, then how much of each, the bypass and the treated flow rate, should you have? Like, what should the mix be if your overall target flow rate is going to be 65 liters per second? And so that mass balance approach just relies on, there's 2 equations and 2 unknowns. And one of the equations is already shown on the screen here, but then the other equation is that Q treated plus Q bypass is equal to Q of blended. And so in this example, what I did is I isolated one of those. I said, let's write the treated flow rate in terms of the blended and the bypass. And it's the blended flow rate that we actually know on a quantitative basis. And then we can substitute it into this mass balance equation and find out how much of the bypass flow rate there ought to be, and then therefore how much of the treated flow rate would you combine together to get the blended flow that gives you the combined concentration that you're aiming for. So it's just a refresher of that mass balance approach that you've seen in other areas as well. Okay, so now I've got 2 minutes to talk about membrane separation. And I think the most valuable slide is maybe this one. Membrane separation is a process that uses pores, like the physical separation of particles that are in water. And so in the case of microfiltration, it's just a membrane that has holes that are small enough to filter out bacteria, algae, any particles that are bigger than 0.1 micron are stopped, and water molecules and everything else passes through. Now, ultrafiltration, the little holes in the membrane are small enough that now it's going to remove viruses and small colloidal particles, like small particles of clay. But then everything else passes through, everything else like ions, for example. In the case of reverse osmosis, you progressively have smaller and smaller ions, and among the most difficult ions to remove from water, unfortunately, are sodium and chloride. And that's unfortunate because in a lot of really dry, arid areas where they have to desalinate water, it requires really intense pressure. You need a lot of pressure to get water molecules through this porous membrane, but everything else to be rejected, like up to 4,000 kilopascals, where typically the water pressure that we'd have in our pipes in an ordinary water network like we've got here in Huntington would be maybe up to 850 kilopascals. You have to have more than 4 times that much pressure to push water molecules through a reverse osmosis membrane. So reverse osmosis is just kind of a specialized process that it talked a little bit about in one of the videos I shared with you during our earlier lectures of the semester. But we're out of time for today. Look for homework 3 to be posted in maybe the next hour, and then that'll be due on Friday. And then in class on Wednesday, we're going to have a little quiz just as an appetizer to the test that's next week.